Hello, in this problem solving worksheet I'd like to do an example that actually is in the book, but this is complex enough that it's really worth me doing it in person, so you can just look at what I do and see how you can do such problems. So the figure shows a tin uniformly charged rod of length L with a total charge Q, and they were asked to find the electric field at a radius R, at the radial distance R, and the plane that bisects here. So actually straight in the middle. So this is a tin rod. So when we have a tin rod, we're essentially going to treat this as a one-dimensional object. And we have a total charge Q. The length of the rod is L, so we can talk about the charge density lambda, which is going to be Q divided by L. Okay, so this is the amount of charge per unit of length. Okay. All right, so let's try to visualize this. We want to find the electric field at R. They say electric field strength, so probably just a norm would be fine, but we have to find the direction anyway also. So let's visualize this. Let me redraw this. This is my rod. I'm going to make it pretty thick, but really it is tin. And then this is going to be the X direction. This is going to be the Y direction. And we want to know the electric field at R. I didn't draw this right, but this is L over 2. So this is right in the middle. Okay. So if the idea is that this is a uniformly, the charge is uniformly distributed. So we're just going to take a little piece here of that object here. So it has some small charge delta Q. And then let's find the electric field from that. That's the idea. Then we're going to do it for all the others, and we just need to sum. And since there's going to be, it's uniformly distributed, the sum will become an integral. So if I just look at this is a small, essentially point object, so I can use Coulomb's law to find the electric field. So this will create an electric field here. The charge is positive. It's positive charge everywhere. So the electric field will be pointing away, directly away from here. So this is going to be the electric field, let's say delta Qi, this charge I here. And there's going to be this, the value of the electric field will depend on this distance Ri. Okay, so I can then just kind of use Coulomb's law to find this electric field here. Alright, so let's do that. So EI, so first the magnitude of EI from this little charge here, I can just use Coulomb's law. So I can just go to my formula sheet, see if it's a point charge, that's the electric field. So it's equal to 1 over 4 pi epsilon times delta Qi, which is my little charge, amount of charge, positive charge here. And then I am going just to divide by the distance square, so Ri squared. Okay, so that's the magnitude. And then I can go and calculate each different charge will create a different magnitude, but then I need to sum all of those. The problem is that you need to sum them as vectors. So I really need to find the vector version of this. So, well, let me just write this as a vector. I can tell the direction here. So EI is going to be this magnitude to Qi over Ri squared. And then let's call this angle here, say theta I. It's going to be different for different little point charges. Then this is going to be cosine theta I in the I direction. And then minus sine theta I in the j direction. So that's the vector. It has an x component and a y component. And the idea is to find the total electric field. I need to sum all of these EI's vector for the whole bar. Okay. Now, very often when you have such problems, you can save a lot of work by thinking. See, this vector looks good. If I have a small charge here lower, there will be a different theta I, a different Ri. If I'm in the bottom here, if I look at a charge here, see delta Q, another Qi, then this will create an E field this way, right? So if I'm at the bottom, I create an E field that still has a positive X component, but now instead of having a negative Y component, it will have a positive Y component. So what I can see here is when we use this in physics a lot. It's called a symmetry argument. This by symmetry, the y will cancel pairwise. Will cancel when this one plus this one are added together. There won't be any y components. So at the end, I expect when I have a charge like this and I'm asking for the field right in the middle, my expectation is that it will just be in the x direction, because the y from this one and the y component from that one will have cancelled because they're in opposite direction. So at the end, I expect that the E field just has an x component. Okay. This is a really important step to do, because essentially you could go and calculate EY, but it's, it'll be a lot of work, and at the end you'll just find 0 if you do it right. So you can save work by just thinking it through. So then I just need to know EIX and then sum those guys, because the x direction, everyone gives you an x direction to the right because it's all positive charge, so they all want to put an electric field to the right. Okay, so what is EIX? Let me rewrite this. So I said it's 1 over 4 pi epsilon dot delta QI over RI squared. This is just Coulomb's law. But in the x direction, I don't need the whole thing. I just need the x component. And that is truly the same for all the charges on the bar, but all the charges on the bar will have a different angle. For example, the charge here doesn't have an angle, it's just 0. And they will have a different direction, distance too. Some of these charges are farther away than others. Okay, so these two depend on that. This delta QI, I put an I here, but actually it's all going to be the same. I can take the same amount of charge for each little object. In fact, what is this delta QI? Let's do this part. So the step 1 was to realize that by symmetry, all the y direction cancel. Go back. So step 1 was really important to realize that there was nothing in that j direction. Then step 2, I need to write this in a way that I can make an integral. And the trick is to write delta Q in terms of the charge density. So this is a linear object, so I can write this as lambda, which is the amount of charge per unit of length, times the length, and this is a small delta y. Okay. So in this bar, delta Q is going to be the amount of charge per unit of length times delta y, and the amount, when I take delta to be very, very small, infinitesimal, then we use these dq equal lambda dy. Okay. So this is the amount of charge for each little bit of the bar. Great. And so that's great. So I'll just rewrite that as 1 over 4 pi epsilon naught lambda here dy, and then cosine of theta I over Ri squared. Great. That's EI. And then if I want to find a full E field, I'm going to just integrate this. This is a constant, I can take it in front. From y equal minus L over 2 to L over 2. Okay? Because this bar goes from minus L over 2 to L over 2. And that will be the full EX. Okay? Now the thing is, though, this Ri squared and theta I squared probably depends on y, so I need to look at that. Let me redraw this here. So the situation is x equals 0, well, x axis, this is the y axis, and then I have my EI field here, and this here is Ri, this here is the coordinate yi of the little piece here, and this was my angle theta I, which is exactly the same as this one, because they're just on the opposite side here. So I can see, and this distance is known, this is r. This is what they're giving us in the problem. I'll show you here. They say find the electric field at distance r, which could be 1 meter or 1 centimeter, I don't know, but it's a fixed known distance, r. This is where I want to find the electric field. So this is this distance here. Okay, so then let me write, so for example, Ri is the hypotenuse of this triangle, so Ri is y I square, or let me just call this y, not yi. This is y square plus r square, and the square root of that. While theta I, or cosine of theta I, which is what I'm going to really need, this is the adjacent side over the hypotenuse, so it's r over ri, with ri given by that. So then when I rewrite that all together, I'm going to get that the electric field in the x direction is equal to a constant times an integral from minus L over 2 to L over 2 of dy, and then times a something, and that something is cosine over that square, so that's r over ri cube, and the r also is a constant, so I can take it out, and ri cube is, so this is lambda r 4 pi epsilon naught minus L over 2 to L over 2 dy over r square plus y square to the 3 half. Whew, that's it. Once you're at this point, then you can breathe. It's all the thinking has been done pretty much. Then it's just doing an integral, which is not easy, but it's just still, now it's just math. So the x component of the E field was the sum of all the contribution in the y direction, which became an integral over y, and then r was a constant, so I took it out, and I get this r square plus y square, and I get to the 3 half. 3 half because I got 1 over ri from the cosine, and I already had 1 over ri square from Coulomb's law. Okay, so then you go take your book. In the exam, this would be given. It says this is what kind of integral? This is appendix A, and this is an integral, this one, where we replace x with y, so this is dy, y square, and this is a plus for us, so it's y square plus r square to the 3 half. So I'm going to use that to rewrite this here as lambda r over 4 pi epsilon. These are all just constant. And then this integral becomes y over r square times the square root of r square plus y square. And this will be evaluated between y equal minus L over 2 and y equal L over 2. So the r squared comes out. So this is going to become lambda over 4 pi epsilon naught times r. And then this becomes L over 2 square root of r squared plus L squared over 4. Then minus, this one is also minus, so that's great. So that's minus, minus. Become a plus L over 2 r squared plus, and then this square is L squared over 4 again. That's a square root. So both terms are exactly give you the same contribution. So this is what, in the y direction, you would have found that the contribution from the top would have one sign, and from the bottom would have had the other sign, and you have get in 0. In the x direction, both the top and the bottom gives you something to the right, and so they both give you the same sign, so you just get a factor of 2, so the 2 here cancels, and so we end up with lambda times L over 4 pi epsilon naught times r, and then times the square root of r squared plus L squared over 4. And that is the answer. That's the electric field in the x direction, which, since there's no y component, is the full thing. Alright, so this is again done in your book, so you can look at your book again also. It does take practice. I know this is scary, but it takes practice. Note an interesting thing. Maybe we can assess this quickly. What would happen if the bar was really long? Let's say L is very large, goes to infinity. So L is much, much greater than R. That's true, then let's say L is 100. So this is 1 plus 100 square. So this can be dropped. So in this limit, this will become lambda times L over 4 pi epsilon naught times R, and then this square root just becomes L over 2, so I can send the 2 up there. The L cancel, and I get lambda over 2 pi epsilon naught times r. So this is the infinite line answer. If you go to your formula sheet, the electric field of an infinite line is 1 over 4 pi epsilon naught times 2 lambda over r, where lambda is you take the absolute value and the sign, your direction decides if it's positive it's away, if it's negative it's toward. In this case we did it positive, so it's away, so this is positive. That's exactly the answer. So that's great. So that means we know we did the right thing, because this is the more complicated if the line is not infinite, but we see that if the line is infinite we recover the result of an infinite line. Do not hesitate to ask questions about this video on the discussion boards and elsewhere, and make sure you look at the examples in your book. Thank you.